So I wanted to talk today about um, 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 this one. This is magnetic circuits, and we kind of went through that in a hurry. And I told you a few things that I know about magnetic circuits, and that's as far as we went with it. And I want you to understand that if you want to go back and learn more about them, that's fine. But today we're going to talk about transformers, and we're going to go through them rather quickly because my understanding of transformers is really kind of limited. But I've never felt like I was limited because I always was able to do what I needed to do with transformers. And the way that I teach them in my classes is basically transformers are easy. They're not. There's more to them than what I put into it. But you know, you can get along in life if you sometimes don't know every little thing about something, but you know enough to stay out of trouble, and that's pretty much where I've been with Transformers. Is I've stayed out of trouble, but I've never really some of the stuff in Transformers. I've never really tried to understand all the gory details. So basically, if it's an ideal transformer, we know that. Okay, if it's ideal, that's good, okay? If it's not ideal, then you start getting into all this other stuff. And I'm not going to go through all the stuff we've talked about before with transformers. Um, but anyway, down through this chapter, you look at some of these models of transformers and you say, oh my goodness, here's some of the models that they come up with. And we could have some problems with that if you wanted to, but I'm not going to. Um, I could ask you some problems along this stuff. And you could say, thank you for not having that on any kind of a test or anything. But now, when somebody does commission a large transformer, they do two tests. And they do these two, open circuit and closed circuit. So these are the two tests that you would see somebody come and do. Now, that's not necessarily something that you would do. Now, if you were a power engineer, this is right down your pike. You would do these two tests, and I've seen the people that have done these, and I know what they basically go out there and they do some measurements. They do an open circuit, and they do a closed circuit. And you say, how could you possibly do a closed circuit test when you short the secondary on a transformer? Well, they use a reduced voltage is what they do, but they do have a test for a closed circuit. Okay. So again, I don't want you to panic when he says um, there's an open circuit test and a short circuit test, and they do both. Okay. Now here are some of the connections for a transformer, and here's your single. Uh, they call it single. They call it two-phase, but I'm going to skip that one. Three-phase delta to delta, three-phase delta to Y, Y to Y, and an open delta. Okay. And then this would be a something else, and this would be a to a six-phase. I've never heard of that one, but that's another way of saying ouch. Typical, most of them would be delta to delta, delta to Y, Y to Y. Now, why would we use these varieties? Well, usually if you use a delta to Y, you decrease the harmonics. They say that you decrease the harmonics more. So that was the typical way that I was familiar with it when squaring fiberglass. The secondary has a grounded middle position, and then you would have three phases. Now, in anything that you use, this is, and I've drawn this many, many, many times, and you've seen me draw it many, many, many times. You have three phases: when it goes out like this, when it goes like this, and when it goes like this. And they're out of phase with each other by 120 degrees. So you can represent the three wires, either this delta would be from here to here, from here to here, and from here to here, and the Y is from the middle out, okay? All right? But if you wanted to look at the voltage from here to here, like this would be 470, this would be 480 volts. This would be 277. What's the ratio? What's the difference between these two? It's the square root of 3, isn't it? So that this is a value, this is a value, and these are the, when you measure, you're measuring from here to here. You're not measuring from there to there. Now, you could measure from there to ground, but you may not have a ground that you could actually measure to, other than the water pipe. But you measure voltage phase to phase, 480, and then the phase to ground is 277. The relationship is square root of 3. You can also find this in other flavors. You can find this in, this would be half of that, 240. This voltage from here to here is 240. And this would be half of 277 or 133 or whatever. But that's another way of doing it. Now, most of the time they use 480 because you can get a smaller wire gauge. This is a little bit more dangerous to use, but most companies use 480 volts for your motors, okay? Why do you use three-phase? Why do you use that? Two reasons. One is it's more efficient. The other reason, single-phase motors tend to walk. If you put a single-phase motor in a plant, somebody will find a reason for it to get trashed, and then it goes out in the trash bin, and then somebody at night comes out and steals it. So if you can use three-phase, that's not something that most people have in their homes. So they tend to, even though they're maybe a small motor, they tend to not be as easily dismantled and taken out. And that's why they use air motors in a lot of plants. That air motors are hard to, you know, not hard, but you just, most people don't have them, and they don't find a reason to take them out. Not to say that everybody is dishonest, but the idea of using three-phase motors is they're more efficient, and also they have this idea of most people don't want them. They're not something that you would have in your household. Okay, now there are others. There is .208. Excuse me, this is 120 here. So this is 120, and this would be phase, and this would be 120, and this would be right here, would be 208. Now, where does this come in? A lot of places. It comes in our school. Okay, so your phase to phase value is 208. Your phase to ground is 120. And that's what we have in school over in, that's where they have it a lot of places in our school, okay? So in labs, we have that, and it's just, if you need 120, phase to ground or phase to zero. If you need three-phase, you've got it if you need it. Now, what is the difference between 208 and 240 or 230 or whatever's the difference there? 15 volts, 20 volts. That's enough to cause motors to not work, but most motors and most circuits now will work with either 208 or 240. Okay? So you can get a motor that will either turn at 240 or 208. And if you don't, how do you get 240 out of 208? Now what? It's called a buck boost, which is nothing more than an auto transformer. We'll do that. So you always have to be careful. Is this a inverter or something that will work on 208, or do you have to go to whatever? But if you can, Usually most things will work on either 208 or 240. You got to be very careful. You got to watch and see whether it'll work on 208. If it does, you're good to go. If it doesn't, you have to do something about it. And a buck boost transformer, an auto transformer, will do that. Now, what is an auto transformer? Well, it's a transformer that looks like this. There's your one tap and there's your other tap. Okay, so here would be your primary, here would be your secondary. I've drawn this out many, many, many times in class, and I've asked the question, here's my I going in, and here's my I over here, right? Well, this is a lower voltage, should be sure, this will be a higher current. So this would be I1 and I2. I2 typically is higher than I1. Yes, how could that be? Well, it's basically because you can have vectors. You can have an I1, and you can have an I2, you can have an I3. You can answer questions with vectors. You can never answer just straight out with addition of numbers. So again, I'm giving you some hints as to some of the strange things that can happen, but an auto transformer can give you that. It can give you some strange phenomena, whatever. But it works. Okay. What else can we do? There are constant voltage transformers. There are transformers that will have that will bring up voltage. They would actually do that will find the right voltage, and those are very not dangerous to use, but they're if you have a lag in your voltage supply and you need to be able to come up to an exact value, and so there are these transformers that will actually do this based on what your voltage is. The application of those, I did one time, and it sat there and went like this, and it didn't work. And it was basically constantly hunting for the right value. So again, usually you don't have these problems anymore. If somebody says, well, you have to have the exact voltage, so they will find you a like a self-tuning transformer, that type of thing. The only one that I ever bought didn't work. I'll be blunt. So again, I'm just giving you my own experiences, and I'm telling you that I've never run into that again, and I only had to do it once. And I sat there and did this, and we got rid of it. I don't know exactly what we did with it, but I'm just telling you, be very careful when you apply those, because they can sit there and do this. Embarrassment, yes, sir.
Is there a difference between like for the buck boost, is there an AC and DC, or are they both the same thing?
These are all AC. Everything with transformers is AC. Everything with transformers is AC.
There was a buck boost for DC circuits.
Well, you can have a buck boost for a DC circuit, but it's not the same.
It's different.
It's a very different device. The buck boost for the AC circuit is this guy right here. For the buck boost for the DC circuit, you're actually storing values on a capacitor and then adding it. Yeah, you're using a capacitor to move. You have a small DC value and you want a higher DC value, and they use capacitors to get you up. They store it and then they flip it. That's DC. There is a DC buck boost, but it is not the same as an AC. Yeah. If anybody ever sends you for a transformer for a DC circuit, they're pulling your leg because they don't work. Transformers only work with AC circuits. Everything is based on the change in flux, the dphi over dt, with respect. I can't write anymore. This is embarrassing. Change in flux with respect to time. Okay, change in flux with respect to time. If there is no change in flux with respect to time, there is no voltage. Okay, that's equal to voltage. And if there is no change of flux, there is no voltage. Anywho, that's okay. Now, what else? You got buck boost. You've got okay. So sizing of transformers. I have a PLC project with 2,000 outputs, 1,000 inputs, and and they're all in this control panel. Okay. Now, maybe I could say 200, or I don't really care, but let's just make it big numbers. Okay. So do I find the maximum power of each of these outputs and the maximum power of each of these inputs, add them all up, and then buy a transformer that's bigger than that? Is that what you'd say? To be safe? No. What do? You actually have to look at the rating of the devices. In other words, what is the current input or output of those devices? And then multiply it by that number. In other words, if you have an output, a solenoid, that has a runtime current of 0.2 milliamp or 0.2 amps, and you multiply that times that. If you have, now here's a question. Are you going to turn these all on at the same time, and are they all going to have an inrush? Then you have to go with the inrush current. But most of the time, you don't have to turn them all on at the same time. So then you just go with the standard. So you don't go with the inrush, you go with the standard, unless they all have to be turned on at the same time. Valid question. You have to ask that. But if they don't all have to be turned on at the same time, you go with the running current of the devices. Multiply that times the voltage at which they're output at, 110 volts or whatever, and that comes up with a wattage. And you add all your wattages together, and then you buy the next biggest size. Basically, you add plus 20%, 25%, and go to the next biggest transformer. I've seen this, and people have actually put huge transformers on panels. They set them on top of a panel, and they don't need that much. And the reason is because they went to the maximum output of each device. Don't do that, because it's about 2 to 3 times what your actual running value is. So the other way to do this is to look at what other people have done and do the same thing and hope for the best. That's another approach, and that usually works. It may not work, but people have been laughed at, but never totally shot down if they go too big. If you don't go big enough, then you can not only get laughed at, you get fired. So again, the old expression, nobody ever got fired for specifying IBM. And that's true, I guess, up to a point, and then eventually IBM lost a lot of their market share. But it's true that if you go a little bit big, you're never going to get fired, as opposed to if you go too small, then you will get fired. Or you may not be fired, but you may be. I don't know. It depends. Any questions about transformers and sizing of transformers? Does everybody understand what I just said about transformers? If you have 200 outputs and 100 outputs, 100 inputs and 100 outputs, or 200 outputs, or whatever, you have to go through and do that calculation. You have to. If you don't, you'll get the wrong size transformer. You got to supply enough power in that transformer to power all the devices that are on at any one particular time. Okay. Again, Okay, so what else do you find of this kind of stuff? This is not in the book. This is interesting. Now, what are these things? What's a watt meter? What's a var meter? Do you think that these exist? Do these exist in the wild, or have you ever run across a watt meter? Have you ever run across a var meter? Okay, so here's the here's the the power triangle. Okay, this is V times I. This is V times I cosine theta. This is V times I sine theta. Now, if you do this with three phase, you just, what do? You add the square root of 3 to each of these, don't you? You add the square root of 3, square root of 3, square root of 3, and away you go. What about single phase? Well, this works for single phase, all right? But now, what does a watt meter imply? That you know theta. Because you can measure I, you can measure V, but you can't measure, how do you measure theta? Any ideas? Any thoughts?
Just give it a standard.
It's not a standard. There is no standard theta. It varies with the load. It varies. It can be anywhere from 10 or 15 to up to 30 or 40 or higher. If you oversize a motor, if you have a 25 horsepower motor on something that only requires 2 horsepower, what do you think happens to your power factor? What do you think happens to theta? It's really big. Okay? Theta goes really through the roof. If you size it 25 horsepower and you use it for 25 horsepower, then your theta is much more, it's much slower. But theta gets bigger based on if you undersize it. Okay, if you're if you oversize the motor for the load, theta gets really crazy big. Okay, but how do you measure it? Watt meter, voltmeter, or watt meter and var meter. How do you measure it? With a watt meter. Okay, but how do these work? Somehow they have to find theta, don't they? They have to do that. So you have to do, these are 3-wire devices. Okay? So somehow you have to measure some kind of a current, and you also have to measure the voltage across. You have to measure both somehow. They're a 3-wire device. Okay? Both of them. And then you just have to look at the directions to see how they hook them up, because they all hook them up different. Now, what's really strange is there was a company down in Bluffton, Ohio called Triplet. They were around for years and years and years and years and years before they went out of business. Okay? Triplet Meter Company. And they had these with no, they were all with this, there were no transistors, there were resistors in them, but I don't know how they worked because they did not have any transistors or any solid state componentry at all. They were all just windings. Okay? Now you can research how Triplet did that, or you can say, well, I don't really care. I just have to measure I and I have to measure V, and I can look at the phase shift, and there's my theta. You can put these in a little computer system and you can measure it that way. Or you can say, the heck with it, I'll go back to the Triplet method. I don't know how they did it, but they did it. And somebody in their infinite wisdom threw away all of our Triplet watt meters. We had a potload of them back in the day, And somebody went through in their efficiency moves once upon a time and said, "What are these things?" I wasn't around, or I would have squirreled them away because I didn't know what I had, but daggone it, triplet watt meters were the gold standard. And you could look at those and they would, on a panel, but they were three-wire devices. They have to be three-wire, okay? They have to be three-wire to measure the current and the voltage and look at the phase shift between them. But, you know, you may look at them and say, that's not so hard to do. Or you can chat GPT it and says, how did they do that before they had solid-state devices? Today, they look at them with, the Chinese have these little devices now that do this, and they mimic that. They put triplet out of business, I'm sure, but all I know is when you say var meter, watt meter, what are you looking at? Is it a meter that's got two wires on it, and so you got to just hook up two wires? No, it's a three-wire device. I learned that much, and I've had to hook enough of them up that you get hammered in your head every once in a while, you know, that's what it is. But what you're actually looking at is you're looking at this right here. You're not looking at this, you're looking at this. What does the var meter look at? It looks at this, okay? Any questions about those things, what they mean and how? Okay, so will you ever have to hook up a var meter or a watt meter? Probably. And when you do, look for the third wire. It won't work unless you have three wires, okay? Any questions? That's about it. Okay, let's go back. So now I'm going to go to Gus. Okay. Gustafson. And I numbered the pages. What will you think of next? So this is the starting of the Gustafson on power generation and instrumentation. So that's where we're at right now. Okay, so I want to make this as big as possible. So you can see it.
In the bottom right, there's a magnifying glass. All the way to the right. The right bar. Keep going right. It's,
Okay, thanks.
Yep.
Thank you. Okay, so we're talking now about power and how you get it, and then what you do with it is the next phase. Okay, so you have to have a generator of some kind or some way of doing that. Well, here's a battery. That's one way of getting. It's one way of getting electricity, and the other way is by generating of it by some kind of something in a power plant. So that's how you get electricity. You get it through a power plant. Okay, and that's what that's about. Okay, now that's it until you get it back to your house or your farm or whatever, and at that point in time you have what they call a service entrance, and you basically have what? This is the basic what most people have in their homes or on most areas. Now that does not include three-phase. This is single phase. What does that mean? You're basically doing what? You have two phases. Really, it's one like this and one like this, and they're 180 degrees out of phase with each other. One's going up while the other one's going down. So if you look at them on a scope, this guy's going like this, while the other guy is going like this. All right, they're just exactly out of phase with each other by 180 degrees. So what does that give you? Well, it gives you the ability in most applications to either get 120 degrees or to get 240 volts, either one, single phase, that's it, okay? The grounded neutral. That's single phase, okay? It's what you got in your house, most likely. And it is that's what everybody has, pretty much. Okay, now, when you have the circuit breakers in your panel, you can either have ones that go from the middle to outside, or they go from the outside to the outside. These are your 240 breakers, and these are your 110 volt breakers. This would be the three phase. This would be a delta to delta. You can also have what we talked about before, delta to Y. And you can also take off of the three phase, you can take, this would be your 240 or 480, and then the secondary would be, again, you can go from three phase to single phase by doing this. One of the ways of doing it. Now, when you do this, what have you done? You don't have a balanced three phase anymore, do you? You've actually used this down here to do some extra work, but you've now, unless you have one over here and one over here, you do not have a balanced three phase. What does that mean? It means you have different currents going through your three wires. So this would be an unbalanced system. All right, again, that's a Y to a Y. And talks about grounding. We're going to talk about grounding more later. But here's their pictures um, of your system. Now, this would be an improperly grounded system. In a plant, you can have an ungrounded system. You can have an ungrounded 110, which basically is this. You can have and it's kind of a weird thing, except for the fact that LOF, the company over behind the what you call it, use it. So basically, it's like this: you have a one there, one here, and one here, and this distance is 120. And they have a neutral, and what they do is they put a light right here. Light right there. And if you walk into a plant and all three of your lights that are up, they're in a little box, a little tattle box over your power system. If those three lights are all kind of dim, there's no problem. If one of those lights is out, it means you have a ground at that point. In other words, you have a ground here or here or here. Okay? Now what that gives you is that ground is a bad thing. It's a wire touching a conduit, grounded something, someplace it's grounded. So with the LOF system, and this is in the National Electric Code, you can actually have this National Electric Code. They actually will let you can still run your process with one ground, one bad thing, one thing that does not, that is irregular or won't work. And it's your job, it will be your job if you work to the LOF plant over in Rossford, behind the Hollywood Casino, and they have this to this day, I'm pretty sure of it. They have that system. So if you were to walk in that plant and see one of these lights out and the other two lights pretty brighter than they normally would be, what you have is you have a ground either here or here or here, and it's your job to find it. So people actually go out and they turn off various machines while they're still running. So you selectively turn something off, turn it back on, see if the lights go back normal. And if that's lights go back normal, that means that that ground is on that that circuit. And you keep trying this until you find the right one, and then you go down to the actual device and you look at it and you try to find out what is wrong with it while it's still running. And if you can, you've kept your system up and running. So that's the goal. The bad side of that is what? You're trying everything while you're still running. The other bad side of that is that for every circuit, you have to find its neutral. In other words, if this right here is the plus, this would be the negative. You've got to go back into the panel and find the neutral for that circuit. And it ain't always easy. You can't go to a water pipe. It doesn't work. You cannot go to some simple system ground. You have to basically find the neutral for this circuit. And there's a lot of circuits, so you have to go find the right one and then use that as your neutral. Drag that neutral over to where you have to check it out with your meter, and then you might be able to get lucky and get it to work. Otherwise, it's a painful process. But you have to find the neutral. You have to find the right neutral, and they're not easy to find. But if you do, you can keep the system working without another ground. Now, if you get a second ground, at that point in time, everything shuts down and you really got a mess. But you can keep running with one ground. The other way of doing it is a grounded system, and if you get a short, it shuts you down. It trips a circuit breaker just like that. One ground, you're out of business. And that's the way Owens Corning ran, which you may or may not like the idea that that's how they did, but that's what they did. So again, you decide, and most automotives run that way, so you decide which way you want to go. This is supported in National Electric Code. It's weird, but it is. You can look at it, and it's a three-phase ungrounded system for control. Now, in a control room, in a control environment, would you ever have this? And now this is what you use in a house, but would you ever use that in a control panel? Why not? Any ideas why you would never put this in a control panel? What would you do in a control panel? You just do this side up here, or you do this side down here, but never both. Why not? Why not use both? Why not introduce 240 into a control panel? You're working with electricians, okay? And when they grab a hot wire, they grab a hot wire. They don't care whether it's off of this this side or this side. So if they grabbed off of the side that your circuit's on, you're in luck. But if they grabbed off of the other side, what have they done? They've introduced 240 into a 120 circuit. And when you do that, what have you done? As soon as their relay closes, what happens to the voltage? It's twice the voltage. What happens? You weld contacts. And you end up with a worse mess than you started with. So again, I'm not saying you can't do that. You can't put one of these systems in a control panel, but you shouldn't for that very reason. And they will do that. Do you believe me? Okay. So this is very useful and it's very good for a house. And you can use it in a plant as long as you don't bring both of these wires into control panel, as long as you just use one side or the other. You're okay. But if you use both sides and bring it into control panel and use one for one set of hot wire, well, the other side of hot wire, they will do that. So be careful. Equipment grounding. Now, where does the electricity go? It goes through your body back to this ground point, doesn't it? Uses a path. So if you are the quickest, you can't beat electricity. It'll go faster than you can. So if you touch something and it's not grounded and it's got a live voltage on it, the electricity goes through your body and back to ground. My dad, he's dead, but his grain bin has a short, not a short, but one of the parts is ungrounded right now, and I don't know which part it is, but you can be touching the motor, not the motor, but the starter for the motor, and then you can be touching the grain bin, and you get this poke. Not a bad poke, but a poke. So what is it? One of them is ungrounded, and I bet it's the control panel. I bet the ground wire for the control panel has come off. In 60 years, I would imagine that's probably what's happened. You can just feel it. Isn't bad. It isn't bad, but just enough. And no, I haven't gone out and tried to track it down. Whatever. Okay, enough on that. Okay. Now we're going to get into the idea of how you protect things. And fusing is one way of doing it. And by the way, I am waiting on the folk from the SSOE to come back and give me some kind of a feedback as to what they do. But I will say this about fusing. As you go through and look at fuses, they not only have a current rating, and this is stuff that I've never done. I never had to do this. And if you're in the controls industry, this is just kind of off there someplace. But fuses not only have a current rating, they also have a time delay. So basically what you want to do is you've got this as a trip, this I versus T. So you have one that's got a like this, and then you got one that goes like this, and you got one that goes like this, and you got one that goes like this. Now this should be the farthest one upstream. This should be the next to next. This should be the farthest one downstream. You should be able to overlay your current versus time graphs of your fuses. And this should be the one that trips first, then this one would trip second, then this would trip third, this would trip fourth. If you get these backwards, what happens? The upstream trips before the downstream one does. And you'll have a real hard time finding where the actual fault was. Okay? This is what power engineers do for a living. I can make fun of them. Say, that's what they do. But that's why they pay you to actually do this and look at these and make sure that the fusing is such that they trip in order. They don't trip backwards. In other words, the one that tripped the whole plant wasn't because you were drilling something with your drill. Okay, that happens. You trip the main breaker on a plant because you short circuited something when you were drilling with your drill. That's not good. And if that happens, might happen once or twice, then you get called in and they say, now what on earth are you doing and all that good stuff. I thought it'd be cute to be able to, trip the whole plant off by doing that. They don't like that. People do not like you taking them their process. They just don't. They think that's not humorous. Anyway. Anywho, so these thermal elements in breakers. Now there's more sophisticated than that today, but basically they have to do this. They have to, based on a certain current, they have to trip. Okay? Fuses trip before breakers do. Breakers are slow, fuses are fast. But the combination of the fuses and the breakers have to trip out everything in an orderly way. So if you use a combination of control of circuit breakers and fuses, you really get into a mess because you have some things that go faster and the other things that go slower, and that's where it gets really kind of complicated. So what you hope for is you have a good power engineer, and they have this stuff all laid out for you, and all you got to do is basically from your motor controls down, you don't have to worry about this. But from your motor control center up, this stuff becomes very critical. Okay, so typically the power is distributed to you from a motor control center. So here's this big dividing line between power engineers and controls engineers. It's called a motor control center, MCC. Okay, and on the one side of the MCC, the power engineer is the boss. On the other side, you're the boss, or I'm the boss, whatever. But I'm the controls engineer. Okay, I'm a controls engineer. I take the power from the motor control center and take it out and do something with it. Now, if it's a utility-based thing, lights or whatever, he does, but typically they don't even give you the same motor control center. You got a motor control center for the machine, the process. He's got another motor control center sitting over here for the lights and the pumps that do the utilities and all that kind of stuff. He controls that motor control center. So you don't even control that motor control center. I don't really care. I don't want that. I want water when I want it. I want air when I want it. I want steam when I want it. And let them do that over there. I want what I need to make a product, and that's it. And then I write the programs that make it hum, and we're all happy. But the power engineer doesn't care two hoots about your process. All that he or she cares about is that they've delivered all the things that you need so that that it doesn't trip in a bad way. It trips in an orderly way. That's what they do. And that's what these people are going to hopefully come in and talk to you more about. But that's neither here nor there. But that's exactly what they do. They sit there and they make these curves fit. They make them work. And circuit breakers don't interfere with each other, and other devices don't interfere with each other, and they don't trip bad. Okay? And again, I may find some project or something I can come up with as far as that's concerned. But that's pretty much it. And I'm not going to try to belabor this. But do you have any questions of me? Does this make sense? I dread having to do this every day. If I can't find them, if they don't come over or whatever, I want to dread some of this. But I've got enough information here. It's just, I don't want to beat you up with stuff that you'll never remember. The kind of stuff I'm giving you is stuff that you probably will remember. Hopefully you will, because that issue of 110 versus 220 in a control panel, it'll come up. People will say, now why don't you put 240 in your control panel? And you say, I don't want my contacts welded. I'll look at you and say, you must have gone to the University of Toledo and learned all that from, that guy that had to do this for a living. So anyway, anywho, those are some of it's tricks, some of it's just common sense. But between the common sense and the other part, the simplest thing is the power triangle, and yet it's the most it's the best way to describe what you have as far as voltage. If you can get it back to that power triangle, you're in. If you can understand where the parts of the power triangle come up, you're fine. Uh, Somebody pulls three wires out to in a house. So you've got 12240, and they pull a red, they pull a black, and they pull a white. Okay, and they go out to an area. Now they hook the white to the neutral, but the red and the black go to two separate feeds, and one goes one goes the other. But then you say, well, how can you possibly, one is going 15 amps one way and one's going 15 amps another way? How can you possibly not have but 30 amps on that neutral coming back? Well, I think now that we've done this, you can understand that as one current is going up, one current is going down, and they actually cancel each other out. So the neutral isn't carrying any current on it. It's being canceled by the fact that, well, one's going one way, one's going the other. And if you have a phase shift, that may mess it up a little bit, but basically that's exactly what you got. You don't have to worry about your neutral, your 0 volt carrying hardly any current at all. It's not going to. And that looks odd because it should be 30 amps, but it's not. It's one's going up, one's going down. Okay. Any questions anybody's got? Get your stuff graded, and next on Wednesday you will have your second lab, and we're going to talk about what's up next. But I'll have something for you, but I'm not going to. I don't know exactly what it is yet. But anyway,
Quiz printed, do you want it today or just hold on to it?
the quiz, yes. If you got that quiz, please give it to me. That's another thing we're going to do on Wednesdays is we're going to do that, and those are those are some questions that I can actually ask you coming back down afterwards. But I want you to be sharp on the quiz. I want you to be sharp on National Electric Code. At least know things about it. And you don't have to have a copy of it with you. You don't have to go out and buy one. But I want you to know certain things about the National Electric Code. I want you to have that in your head and not be afraid of it. So anyway,
16-week class, so
you'll be you'll be sharp on this because we'll we'll make you at least know a little bit about it, know where to look things up and that type of thing. And if you get into EC&M and are on their website at all, they drive you to being sharp on the next. Like you don't have to take a course. It's just anyway. Take care.